Okay, welcome to this week's Geometry and Model Theory seminar. Today's speaker is Jean-Baptiste Campesato, and he will talk to us about CEM solutions of semi-algebraic equations.
Okay, so thank you for the invitation. So today I'm going to talk about results that we recently obtained with Edward Biersten and Pierre Millman. So we are all from the University of Toronto. And these results are related to two main problems that I'm going to explain now. The first one being the classical Whitney's extension problem. So the question is the following. Given a function f, which is defined on a closed subset of Rn, how can we determine whether f is the restriction of a CM function or not? So that's a classical question that has been studied since at least 1934. There is a theorem of Whitney that I will explain on the next slides. But this question has been entirely solved very recently by Charles Fefferman in 2006. So he gave a condition which is necessary and sufficient on such a function to have a CM extension, or to be, equivalently, the restriction of a CM function. I won't explain this characterization because it is out of the scope of this talk, but instead, I'm going to be interested in a geometric version of this Whitney's extension problem. So I'm going to assume that the data satisfy some additional geometric properties. So namely, I'm going to assume that X is a semialgebraic closed subset of Rn and that F is semialgebraic. And the question is, how can you determine whether F admits an extension which is not only CM, but which is also semialgebraic, so which preserves these geometric properties from the data. So that will be the first question that I will address. And before talking about the second one, I just would like to mention the classical, the Whitney's extension theorem from 1934. And so we start with X, a closed subset of Rn, together with a family of continuous functions. So here, alpha is a multi-index. So alpha is equal to alpha 1, alpha 2, up to alpha n. Each of the alpha I is a natural numbers, and n is the dimension of the ambient Euclidean space. And if we want to construct a CM function, we need to work with indices of length less than or equal to m. So the sum of the alpha I is less than or equal to m. So we are going to assume that these continuous functions satisfy these Taylor-like condition. So informally, it means that when we fix some alpha, the functions of higher indices behave like the coefficients of the Taylor expansion of f alpha. So that's informally, but that's a Taylor-like condition. And when you have such a family of continuous functions satisfying this condition, we talk about a Whitney field of order m on x. And what proved Whitney is that given such a Whitney field, we can construct a CM function big F, which is defined everywhere on the Euclidean space, and such that the partial derivatives of big F restricted on x coincides with the prescribed f alpha. So here that's simply the partial derivatives as usual. So you take x1, you compute the derivative with respect to x1 alpha 1 time, with respect to x2 alpha 2 time, and so on. So this theorem is a partial answer to Whitney's extension problem, because when alpha is equal to 0, what you obtain is that f coincides with f naught on x. And so that's a partial answer. Nonetheless, that's not a full answer, because So big F is an extension of F naught, but it is not a full answer because this theorem does not only rely on F naught and its values, but we need to have this prescribed Taylor polynomial for big F over X. So we need this additional continuous function. It does not only rely on F naught. As I said earlier, I'm going to be interested in a geometric version of a Whitney's extension problem, and there exists a geometric version of a Whitney's extension theorem. So namely, when the data, so X and the F alpha are definable in some ominimal structure, then we can construct such a F, which is also definable. So this theorem has been proved in 1997 by Kurdika and Pawłowski in the subanalytic case, and then it has been generalized to the general ominimal setting simultaneously by Kurdika and Pawłowski and by Tamwong Tanialak. And I will need this theorem later in the talk. Okay, so the second problem that I'm going to address today is the Brenner-Pfefferman-Ochter and Kolar problem. So we start with a family of functions from Rn to R, so F1, F2 up to Fr and phi, and we consider such an equation. So here the unknown are some functions phi I. And the question is under which condition these equations admit a CM solution. So how can we determine whether this equation admits a CM solution? So that there exists a CM phi I satisfying this equation, such that phi is a linear combination of the Fi with coefficients phi I, which are CM. So this question has been entirely solved by Pfefferman and Nulli in 2014. They gave a condition on the Fi and phi, which is necessary and sufficient to ensure the existence of a CM solution, to the existence of CM phi I satisfying this equation. And once again, I'm going to be interested in a geometric version of this problem. So when the data satisfy some additional geometric properties, so namely when the Fi and phi are semialgebraic, how can you determine whether this equation admits a solution phi I, which is Cm, but not only Cm, but also semialgebraic, so which preserves the geometric property of the Fi. So that's the second question that I'm going to address today. And before continuing, I would like to make a few comments about this problem. So it arose from algebraic geometry. The initial question was to study continuous the continuous closure of ideals. So namely, we start with some polynomials Fi, and we want to determine whether a polynomial phi can be expressed as a linear combination of the Fi, but where the coefficients are simply continuous functions and not polynomials. So that's what we call the continuous closure ideal. And this this notion has been extensively studied, and several other questions arose then, and especially in real algebraic geometry. And one classical question, let's say, is the following one. Assume that the data satisfy, so the phi and the Fi satisfy some additional properties, then does the existence of a continuous solution phi I imply the existence of a solution which is not only continuous, but which satisfy these additional properties? And there are several positive answers. For instance, Pfefferman and Kolar proved that when we start with polynomial data, so when the phi and the Fi are polynomials, then the existence of continuous phi I satisfying this equation implies the existence of semi-algebraic continuous phi I. There is a Regulus version, but only the two-variable case, or more generally for Regulus functions on smooth surfaces by Kuharj and Kurdika. So a Regulus function is a rational function that can be extended continuously on the everywhere on the Euclidean space or plane here. And so Kuharj and Kurdika proved that when you start with Regulus function, so continuous rational functions, phi and Fi, the existence of a continuous solution, so the existence of continuous phi I, implies the existence of Regulus solutions. Nonetheless, we also have negative results. So Kolar and Novak gave a counterexample in the three variable case of the previous theorem. So we cannot generalize Courage and Kurdyka theorem in higher dimension. They gave an example of an equation with a continuous solution, but without a regular solution. And similarly, Adamus and Seyedeni-Jad gave an example where the data are polynomials of an equation which admits a continuous solution, but no arc-analytic solution. So a function is arc-analytic if it maps by composition real analytic arcs to real analytic arcs, or if it is, let's say, analytic along real analytic arcs. Okay, so that's all for this Brenner, Pfefferman, Ochter, and Kolar problem. So let me summarize the two questions that I'm going to address today. The first one is the one related to the Whitney's extension problem. So we start with a closed semi-algebraic subset X of Rn. And we have a function f which is defined on X and which is semi-algebraic. And the question is, if f admits a CM extension, so if f is the restriction of a CM function, then does it imply that f is the restriction of a function which is not only CM, but also semi-algebraic? So does the existence of a CM extension implies the existence of an extension which preserves these additional semi-algebraicity properties of the data? So that's the first question. The second one is related to the Brenner, Ochter, Pfefferman, and Kolar problem. I'm not going to work with only one equation, but with finitely many equations that I will represent using a matrix. So we start with A, a matrix whose entries are semi-algebraic functions. And we have F, which is a vector-valued functions whose components are semi-algebraic. And we study this equation. So F is equal to A times G. So A is the previous matrix, F is this vector-valued function, and the unknown is G. And the question, once again, is if there exists a CM solution G, does it imply that there exists a solution which is not only CM, but which is also semi-algebraic, so which preserves these geometric assumptions on the data, so this semi-algebraicity assumption. So these two questions have been extensively studied recently, and there are some partial results. For instance, Aschenbrenner and Tamron-Tanialak proved the first question for any n, so in any number of variable, but in the C1 case, so when m is equal to 1, and the second question, once again, for any n, so for any number of variables, but for the C0 case, so for continuous functions. So the existence of a continuous solution implies the existence of a continuous semi-algebraic solution. And their proofs rely on a definable version of Michael selections lemma. Very recently, Pfefferman and Lully obtained another partial results in any regularity now, so for any m, but the proofs only hold on the plane. So when we have two variables, so when n is equal to 2. And the proof is related to the notion of Glaser bundle, but I won't talk about that because I won't use this notion today. And the results that I'm going to talk about in a few minutes, so they answer these two questions in any variable and in any regularity, so for any n and for any m, but they will imply a loss of differentiability. Okay, so let me give the precise statement of the theorems I'm going to talk about. So the first one is the one related to the equation problem. So we start with a matrix A, whose entries are semi-algebraic, and we can assign to this matrix a function R from the natural numbers to themselves, such that if you consider an equation of this form, so A is a previous semi-algebraic matrix, F is a vector-valued semi-algebraic functions. So when you consider such an equation, the existence of a CRM solution implies the existence of a solution which is now semi-algebraic on Cm. So this R is the loss of differentiability function. If we want the semi-algebraic solution to be Cm, we need to start with a CRM solution, but which may not be semi-algebraic. In general, we do not have a closed expression of R. Nonetheless, when the coefficients of A are not only semi-algebraic, but also infinity or analytic, which is equivalent in this case, then we can prove that R is actually an affine function. But I won't talk about this special case today. The second theorem, the second result, which is related to the Whitney's extension problem, is the following one. So we start with X, a closed semi-algebraic subset of Rn, and we can associate to X a function R, so from the natural numbers to themselves, which satisfies the following property. So if we consider a function f, which is semi-algebraic and which is defined on X, then if f is the restriction of a CRM function, then it is the restriction of a function which is Cm, but also semi-algebraic. So the existence of a CRM extension implies the existence of an extension which is Cm, but also semi-algebraic. So once again, if we want the semi-algebraic extension to be Cm, we need to start with a CRM extension. So I'm going to say a few words about the proofs of these theorems. And the first step is that actually these two theorems are going to be special cases of a common generalization.
Jean-Baptiste, can I ask a question before you proceed?
Yes.
This R is a function of X, right? So for any X, you get a different R.
Yes.
Can you say something about how bad can this R be? Like if A is terrible, then this R can be like a function that grows. You can only bound it. Can you bound it somehow? I mean, I guess the conjecture is that in principle, R should be M, right? R of M
I will explain how do we construct this R later. And it
it
will depend on, we will work locally on strata of a stratification and because of, okay,
if you'll talk about it, I will.
But we do not have a closed shape or information about R, except for the first problem, in the case where it is of the matrix is infinity.
Okay.
But we don't have a closed closed expression for this R.
Okay, thank you.
Okay, so next, let me explain how do we obtain the common generalization of these two results. So these slides, so these common the passage from these two results to the common generalization will rely heavily on the resolution of singularities. So first, let me start with the equation problem. So we start with an equation of this form: A times G is equal to F. So A is a matrix whose entries are semi-algebraic. F is a semi-algebraic vector-valued functions, and the unknown is G. And by resolution of singularities, there exists phi, a Nash proper mapping. So let me say Nash simply means semi-algebraic and infinity, or equivalently semi-algebraic and analytic. So by resolution of singularities, we can there exists phi, so a Nash and proper mapping, such that when we compose A with phi, we obtain a matrix whose entries are not only semi-algebraic, but also Nash, so also real analytic. So what I'm going to do first is just to replace X by phi of Y. So I'm going to compose this equation with phi. So A of X, when I compose with phi, will become A tilde of Y, which is a matrix whose entries are semi-algebraic and real analytic, or Nash. When I replace F by F composed with F composed with phi, I will get F tilde, which is a semi-algebraic vector-valued functions. And then, so I get this kind of equation that I would like to solve. So on the one hand, this question is simpler because A tilde is not only semi-algebraic, but it is also real analytic. So we have some additional rigidity on it. But on the other hand, this question is more difficult because it is no longer from, let's say, a question lying in the context of linear algebra, because there is this composition with phi that we will have to take into account. So in one direction, the question is easier, but we also have an additional difficulty that we will have to take care of. Okay, and for the second question, for the Whitney's extension problem, so we start with X, which is a semialgebraic and closed. Once again, by resolution of singularities, we can prove that there exists phi, a Nash proper mapping such that the image of phi is exactly X. So that's the uniformization theorem. And if you have f, a function defined on X, and if you have G, a function defined everywhere on Rn, to say that G is an extension of f is equivalent to say that G composed with phi coincides with f composed with phi. Indeed, the image of phi is exactly X. So to check that G coincides with f on X, it's enough to check that G composed with phi coincides with f composed with phi everywhere on M. So I just replace f composed with phi by this f tilde, and what we can notice is that we get an equation which is very similar to the previous one. So that's a special case when A is actually the identity matrix. So if we are able to solve to prove the theorem for this kind of equations, we will get the answer for both problems, the equation problems and the extension problem. So it's enough to focus at these kind of equations, and that's going to be the common generalization. So we start with a matrix A, whose entries are not only semi-algebraic but also analytic. So Nash. Then we also have a mapping which is Nash on proper phi, and we can associate to this data, so to A and phi, a function R from the natural numbers to themselves, satisfying the following property. So we have an equation similar to the one on the previous slide. So f is a vector-valued semi-algebraic function. A is the Nash matrix from the assumptions. Phi is this proper Nash mapping, and G is the unknown. And the result is that if this equation admits CRM solution G, then it admits a solution which is CM, but also semi-algebraic. So that's the common generalization. And if we prove this theorem, then we will get the two previous theorems as corollaries. So I will spend the remaining part of the talk talking about the proof of this theorem. And before that, I just would like to say a few words about how general are our results. So actually, for conciseness, I stated the results in the semi-algebraic setting, but our results on proof hold more generally if you assume that the involved objects are definable in a minimal structure, which is polynomially bounded and which admits a infinity cell decomposition. So in the statements and in the proofs, you can replace semi-algebraic by definable as soon as the minimal structure that we consider is polynomially bounded, so the exponential is not definable and admits infinity cell decomposition. The reason why we need these two assumptions is to be able to use resolution of singularities to get this phi that I obtained in 2 slides ago. And let me explain why do we need these two assumptions. So first, when we have an minimal structure which is polynomially bounded, using a theorem of Chris-Miller, we can prove that the set of definable C-infinity functions is a quasi-analytic class. So meaning that the Taylor polynomial function is injective. There is no non-zero flat function. So you cannot have a function like exponential to the -1 over x2, whose Taylor expansion at 0 is equal to 0, whereas it is non-zero except at 0 in a neighborhood of 0. So that's the meaning of quasi-analytic. We do not have non-zero flat functions. And that's interesting because resolution of singularities holds for quasi-analytic functions. So when we have an ideal spanned by infinitely many quasi-analytic functions, then we can apply resolution of singularities. And particularly, we can prove the uniformization theorem in a way similar to the subanalytic case, but to the subcausality case. So a subcausanalytic set is simply the projection of, let's say, a semi-causanalytic case, or a function which is a set which is locally defined by inequalities and equalities of causanalytic functions. So by resolution of singularities, we can prove that such a set is the image of a C-infinity definable proper mapping. So a phi, for a function like the phi 2 slides ago. The issue is that we would like to work with not only the sub-causanalytic sets, but with all definable sets. And that's where this C-infinity cell decomposition is going to be of interest, because if we add this extra assumption, then by a C-infinity cell decomposition, any definable set is actually subcausanalytic. So when we have these two assumptions, we can prove that any definable set is the image of a definable C-infinity proper mapping. And so we can mimic what I did 2 slides ago to pass from the two problems, the two results from the beginning to the common generalization. Okay, so that's just a parenthesis for the definable for the ominimal case. So from now on, I will only use the word semialgebraic, but everywhere you can just replace semialgebraic by definable. Okay, so let me explain the main ideas of the proof of the common generalization. I won't give full details. I will only give some ideas, and also I will insist on the places where the loss of differentiability is involved. Okay, so that's going to be a proof by induction. So by induction on the dimension. So let me recall that we would like to solve an equation of this form. So f is equal to a times g composed with phi, and we are going to work above the image of phi. And the main idea is the following one: if we can solve this question, we are going to prove that there exists a B of dimension less than phi of m, such that if you can solve okay, let me repeat that. There exists a B, a closed semialgebraic subset of the image of phi, which is of dimension less than the image, such that if we can solve the question on B, then we can solve the question of phi of m. And then we repeat the process. There exists a B prime, semialgebraic closed subset of B of lower dimension, such that if you can prove the theorem on B prime, then you can prove the problem on B. So each time we are going to reduce the dimension. So of course, after finitely many steps, that will be the theorem will be we will reduce to the 0-dimensional case. So so there is finitely many steps. Nonetheless, what I'm going to prove here is stronger than the common generalization as it was stated, because I'm not only going to work at the level of values, but I'm going to work at the level of Taylor polynomials. So when I say that there exists that you can solve the problem over B prime, actually I'm going to assume that there is a solution over B prime, and up to subtract to, so there is a solution, let's say G over B prime, and up to subtract A times G composed with phi on both sides of the equality, we can assume that this equation is actually flat. That the constant term of this equation is flat. So all the derivatives up to a certain order are equal to 0. And when I say that I'm going to construct a solution G tilde, which is a solution G tilde, that's not only going to be a solution of this equation at the level of values, but that will be a solution at the level of the derivatives. So the derivative of the left-hand side up to a certain order will coincide with the derivative of the right-hand side up to a certain order. So equivalently, the difference is going to be flat up to order k. So let me just repeat very quickly this statement. By induction assumptions, we can assume that the constant term f is flat. So all the derivatives are equal to 0 over some B prime. we have a solution G of some order T, and we would like to construct a semi-algebraic solution, not only at the level of values, but at the level of Taylor polynomials, and which is now not only CK, but also semi-algebraic. And the loss of differentiability is given by this function T.
It's a very stupid question. So K was M before, right?
Okay.
K was little m in the previous slides, right? So this is the order.
K, yes.
Okay, okay.
But that's going to be approved by induction. So
yeah, it doesn't matter, but just the index name is now.
Yeah, but that's not exactly the same, because that's this K, this T is the function for this induction step, and then you have to work with an upper bound of all this T. So let's say that K.
Okay, but K is the level of differentiability you want to solve in each step.
Yes.
Yes. Okay. Yes. Okay.
So I'm going to assume that I have a solution at the level of CTK, and I want to obtain a semi-algebraic solution which is CK.
Okay. Thanks. Okay.
So that's similar to the M, but only for this inductive step. Okay, so let me explain the strategy of the proof of this proposition. So the idea is that you are going to construct a semi-algebraic Whitney field, and then we will apply Kurdika-Pawlowski-Tamon-Tenelak theorem to obtain the function G. As I said, by the induction hypothesis, the constant term of the equation is flat. So I'm just going to assume that the G that I'm going to construct will be equal to 0 on B prime, so where the constant term is going to be equal to 0. And on the complement of B prime, this G will be a solution of the equation, but at the level of the Taylor polynomials, not only at the level of the values. So this notation is simply the Taylor polynomial of degree L of f at A, of the components of f, the same for the entries of A, and we should not forget this composition which is involved. Okay, so as I said, you are going to solve this question we are going to construct a Whitney field in the complement of B prime, which satisfies the equation at the level of Taylor polynomial, and we will extend it by 0 everywhere on B, and that's where there will be a first loss of differentiability. So using resolution of singularities and Loyasevic inequality, we can prove that given a semi-algebraic set B, there exists a natural number ρ, such that if you take 2 points close enough on B, you can join them by an arc whose length is less than or equal to C times the Euclidean distance to the power 1 over ρ. So C here is a constant, is a local constant, and ρ is the same everywhere on B. And because of this ρ, when we will extend our Whitney field, we will have a loss of differentiability. So G is going to be a continuous field that will be a Whitney field of order L on the complement of B prime. But when we will extend it by 0 everywhere, what we will obtain is a Whitney field which is only on order K, assuming that L is greater than or equal to K rho. So if you start with a Whitney field of order K rho on the complement of B prime, the continuous extension by 0 will be of order K. Okay, so that's the first loss of differentiability. That's when we are going to work in the complement on B prime and to extend by continuity everywhere on B. So now I'm going to explain how do we construct this Whitney field G. So first, we want to solve this equation at the level of Taylor polynomial. So we want to solve this equation. So you have a Taylor polynomial of f, the Taylor polynomial of A, Taylor polynomial of phi, and we're interested in a solution G. And I'm going to introduce some analogus of the kernel, but for this problem which is not from linear algebra. So the kernel in linear algebra problem is going to measure how undetermined is the equation, and here the module of relations is in some sense very similar. It's going to measure how undetermined is the problem, or how non-unique is the solution. So namely, the module of relation of order R over a point B is the set of power series such that which satisfy the homogeneous associate equation. So the equation without constant term. So the set of W such that the Taylor expansion of A times W composed with the Taylor expansion of phi is equal to 0 up to order R. So these module of relations is analogous to the kernel when we work with a linear algebraic equation. And similarly, the difference of two solutions is going to be an element of the module of relations. And the second, and as I said, so this G is not unique. And we will try to add some, okay, that's not very formal what I'm explaining, but roughly we are going to add some additional equations in a certain way to make the solution unique, so that we will be able to express it in terms of the data, which are semi-algebraic, to get a semi-algebraic Whitney field. And to do that, there will be a second loss of differentiability, which is due to the Chevalier's function. So let me make that a little bit more precise. Given a natural number L, there exists a natural number R such that we can express the derivative of a solution G of order less than or equal to L, the initial L, in terms of the derivatives of the data as soon as we look at the derivatives of up to another I enough. So if you look at the equation, but if you look at an equation but for the data are regular enough, then we will have some kind of uniqueness, which allowing us to express G in terms of the data and to get something which is, in this case, semi-algebraic. And this Chevalier functions is telling us for the expected order we would like to have, up to which order we should look at the derivative of f. So more formally, what we are going to prove is that when we fix an L, there exists a stratification of B. So a stratification is a partition, but such that the strata glue in a very nice way, meaning that the boundary of a stratum is made of a strata of lower dimension. And over each stratum, we will have this Chevalier function. So we will associate to L this R, such that when we look at the module of relation for an order R large enough, when you look at the truncation up to degree L, so when we just look at the truncation of the element W up to order L, we won't lose information as soon as we look at R big enough. So that's more precise. That's what I explained a little bit informally on the previous slide. And that's what is going to give us this kind of uniqueness informally. And the issue at this step is that that's a punctual notion, because over each B, we have a module of relations, but what we want is to construct a Whitney field. So we would like to construct something which is uniform. And to achieve this step, I'm going to divide with respect to the relations. So I'm going to use something which is very similar to Grobner basis, and which is related to Hironaka's formal division. So that's a generalization of the Euclidean division. So, but I'm going to divide a power series by finitely many power series. So I would like to express f as the sum of fi qi plus r, such that this expression is unique. So to obtain uniqueness, we will need to replace this condition on the degree for the usual Euclidean division. So since we work with power series, first what we're going to do is to work with the order instead of the degree, and I will need to explain a few things to be able to obtain these uniqueness. Okay, but first let me fix a few notations. Actually, I'm going to work with vector-valued power series. So this notation is simply a very concise way to express a vector-valued power series. F alpha j is actually the coefficient of degree alpha of the jth component. So that's all. So F alpha j is the coefficient of degree alpha of the jth component of F. Hence, the space of exponents is this one, so n to the n times 1, 2, up to p. And we can totally order this space as follows. So we just look at this lexicographic order. So first, you look at the full degree of a monomial. In case of equality, you look at the component number. And then you look at the degree variable per variable. In a way similar to the Newton diagram, we can define the support of f. So that's the set of exponents with a non-zero coefficient. And since we have a totally order, since we have an order, you can define the initial exponent of f as the minimum of the support of f. So the lowest exponent, in the expansion of f. Okay, so let me state these Hironaka's formal division theorem. So we start with vector valued power series, phi 1, phi 2, up to phi q. So I'm going to divide with respect to this phi I. And in order to obtain this uniqueness, I will use this diagram that I'm going to explain in order to obtain a condition that will replace the degree condition for the usual Euclidean division. So first, I start with phi 1. I take its initial exponent. I put it in the space of exponents, and I take the first quadrant coming from this point. So everything which is above and on the right. So on this drawing, I assume that n is equal to 2 and j is equal to 1 because I only have a two-dimensional screen. But but it generalizes easily for a higher p and a higher n. Then I repeat this process with phi 2. So I take the initial exponent of phi 2. I put it on the diagram. And I take everything. I take the first quadrant coming from this point, so everything which is above on the right, except the room that was already taken by delta 1. And I repeat with phi 3 and so on. At the end, I will have a diagram of this shape, actually a finite Riemann diagram, one for each j. And the complement of this diagram is going to be very important for this talk and is going to be denoted by delta. And then the theorem is the following one. When we have a vector valued power series, it can be uniquely written as the sum of the qi phi I plus a remainder as soon as we add these two additional properties, which is that the support of, when we shift the support of qi by the initial exponent of phi, it stays in delta I. And very important for the remaining of this talk, that's analogous to that's analogous in the Euclidean division to the degree of the remainder is less than the degree of b, of phi. We are going to we add the condition that the support of the remainder should stay in the complement of the diagram. So this delta here, the area which is in light gray. And with this theorem, we can obtain something which is very similar to the notion of Grobner basis. So we start with a module M. So that's a module of vector valued, a submodule of vector valued power series. For every non-zero element of M, I'm just going to put its initial exponent on this set. But since that's a module, it is closed by a scalar multiplication. So if I have this point, I can multiply it by y1, and I have the point on the right. Similarly, I can multiply by y2, so I have the point above, and so on. So because of these, because a module is closed by scalar multiplication, these objects, the diagram of initial exponents, look like that. So it looks like the union of the delta I from the previous slide. Particularly, it has finitely many vertices. So these dots here, which are defined in, they have a very precise definition, but I'm not going to give it. But there are some special, finitely many special elements, these dots, that are the vertices of the diagram of initial exponents. And for each of these vertices, I'm going to take a representative. So an element of M whose initial exponent is exactly the vertex. And then we have this corollary, which is a consequence of the Hironaka's division theorem. So there are several important points in this corollary. The first one is that these phi I are actually generating M, and a formal power series is in M if and only if, when we perform the Hironaka's formal division with respect to the phi I, the remainder is equal to 0. And that's not too difficult to see, because so when we look at this formula, if we know that R is equal to 0, of course, F is the sum of the Qi phi I. The phi I are in M. They are closed by scalar multiplication and by addition, so F is in the module. And conversely, if we know that F is in the module, then F minus the sum of the Qi phi I is equal to R. So R is an element of the module whose support is entirely in the complement of the diagram. But by definition, the only element of the module whose complement is outside the diagram is going to be 0. So that's how we prove these two facts. And we can, if we fix some additional conditions on the phi I, actually there is a unique, there is some kind of uniqueness. So the standard there exists what we call a standard basis. So this there is a set of generators which is unique if you add these extra assumption. They are made from this exponent plus a few things which are in the complement of the diagram. Okay, so let me go back to the theorem, and to obtain this uniformity that was missing. I won't be able to assume that the module of relations is actually going to be constant on each stratum, but what we can obtain is that actually the diagram of initial exponents of the module of relation is constant on each stratum up to refining the stratification, of shrinking the strata. So now we have a stratification which is going to be useful in what follows. And if you recall in the induction step, the goal was to prove that if we want to work on B, we need to construct a B prime of lower dimension such that if we can solve the problem on B prime, then we can solve the problem on B. So the B prime that we are going to consider is actually the union of strata of dimension less than dimension of B. So from now on, I'm going to assume that the equation is trivial over B prime. So the constant term is flat over B prime. And I want to study this equation. Okay, so now we have all the tools necessary to construct these the expected Whitney field G. Okay, so let me recall the situation. So we want to solve these equations, so at the level of Taylor polynomials, over the complement of B prime, and by assumptions we have a solution, but which is not semi-algebraic, up to order T. So when we look at the Taylor expansion, this solution is going to give us a Taylor polynomial, WB, which satisfies this equation. So this WB comes from the assumptions, but that's a pointwise. We do that for every B, so that's something which is pointwise, and now I'm going to start from this WB and to divide with respect to the standard basis of the module of relation over B in order to get my Whitney field. So I take the standard basis phi I previously constructed over the module of relations, and I divide WB with respect to this standard basis. So with respect to phi 1 up to phi q, and it's going to give me a remainder Vito, And there are two things which are interesting here. First, Vito, since it is a remainder, its support is in the complement of the diagram. And the second interesting thing, which is that since WB is a pointwise solution, it's a solution over B. When we do the difference, WB minus Vito, we have the sum of the QI phi I. So we have an element of the module of relations. And since WB was a solution of the equation, Vito is going to be a solution of the equation. So we have constructed a solution of the equation at the level of the Taylor polynomials. Actually, we can express Vito in terms of the standard basis that we can express in terms of the data. So Vito is going to be semi-algebraic. And the difficult thing is going to prove that this Vito is going to give us a Whitney field. So it's going to be semi-algebraic because we can express it in terms of the data. And the difficult thing is to check that this Vito is actually a Whitney field. So we have a solution. We have a field Vito which is a solution everywhere, which is semi-algebraic, and we need to check that it is a Whitney field. And to do that, I'm just going to use everything that we introduced before. So we know that Vito is a solution of the equation. So it satisfies this equation at the level of Taylor polynomials. And what I'm going to do is to apply these operators. So I recall that the members of these equations, they are Taylor polynomials. So they are polynomials in Y, but the coefficients are functions. And this operator is simply that dBV consists in taking the punctual directional derivatives with respect to V, so the derivative of the coefficients. And this operator consists in taking the directional derivatives, the formal directional derivatives, so with respect to Y. But we know that the Taylor expansion of the derivative is the formal derivative of the Taylor expansion. So particularly, when we apply this operator to something which is, let's say, regular enough, we will get 0. So when we apply this operator to F, to the Taylor expansion of F, we get 0. When we apply this operator to the Taylor expansion of A, we get 0. And after the product rule, the only thing that we have left is A times this operator applied to V. But that means that this operator applied to V is in the module of relation. But because we have taken some derivative, we lost one order. So we passed from R to R minus 1. But that's not important because of our choice of R, coming from the Chevalets function, if we started with R large enough, actually we did not lose any information. What we have is actually is going to be in the module of relation up to order R, and not only R minus 1. So let me summarize. Let me summarize where we are. So we applied this operator to the field we constructed, and we see that it comes from an element which is in the module of relation up to order R. But we also know that by construction, it comes from a remainder. So the support of G is in the complement of the diagram in the light gray area. But when we take these derivatives, the only thing we can do is to get closer and closer to the axis, because y to the n is going to become n minus n to the y minus n minus 1. So if you start with something which is in the complement of the diagram, after applying this operator, we stay in the complement of the diagram. So we just proved that this operator applied to our field is in the module of relation, but it is also in the complement of the diagram of the module of relations, meaning that it is equal to 0. So we just proved that the partial derivative, the punctual directional derivatives coincide with the formal directional derivative, and that's enough because according to a theorem of Estenes, what I said before, that the Taylor polynomial of the derivative is the formal derivative of the Taylor polynomial as a converse. So that's enough. So thanks to this property, we obtained that the G that we constructed is actually a Whitney field. So we have well constructed over each stratum a solution of the problem, which is a Whitney field and which is semi-algebraic. Now the last step is that we need to glue between the strata, and that's where you will have a third loss of differentiability. Using Loyasevic inequality, we can start that if you start once again with a higher level of regularity, the coefficient of the Whitney field reconstructed, they will go to 0 when we get closer to the boundary, of the stratum. But that's okay, because by assumptions, the constant term of the equation is flat on B prime, and B prime is exactly the lower dimensional strata. So particularly on the boundary of our stratum, the equation is trivial. The constant term is flat. So if you start with regularity large enough, then you will be able to extend by 0 what the vector of the Whitney field we constructed at the boundary of the stratum, and that's and it's going to be okay, since the equation is flat on B prime, so on the boundary of the stratum. So thanks to that, we've just constructed a Whitney field of order k everywhere on B, and which satisfy the equation at the level of Taylor polynomial. So we can conclude using Kurdika-Pavlovsky-Tamonk-Tanalak theorem. So we can associate to this G a function small g, which is going to be ck, which is going to be semi-algebraic, and such that its Taylor polynomial will coincide with big G over B. So particularly, we will have that it satisfies this equation at the level of Taylor polynomial, or equivalently, that the derivatives or this difference are vanishing up to order k. And that's all for the proof. Let me just summarize the loss of differentiability. It appeared at 3 places, but each time that was something which was in some sense either on a stratum or at one step. So we have to be careful that we can obtain a loss of differentiability which is no longer local but global. So the row that was probably a different row for each induction step, but since we have finitely many iterations, you can just take an upper bound of the row. The Chevalier's function, we have a different Chevalier function for each stratum, but since we have finitely many strata, we can just take an upper bound of the Chevalier's function. And similarly, for each stratum, we obtain this Loyasevic exponent sigma, and since we have finitely many strata, we can just take an upper bound of this sigma, so that this loss of differentiability function is well defined. And that's all. Thank you very much for listening.
Well, thank you very much. Any questions or comments?
So I have a question, but it's like a side question, but still. So in the beginning, you explained that the semi-algebraicity will be replaced by polynomial bounded homonymous structures with a nice cell decomposition. And you explained that the proof doesn't work with, for instance, if you put exponent and you don't have quasi-analyticity anymore, and you don't have like resolution of singularities and so on. But the result itself, do you think, is there like an easy example? Like if you introduce exponent and now you look at like Rx, right? So do you have like an example of a function that is, it extends to a, I mean, the result itself, if you have a CM extension, do you have like definable CM extension, or is there like an obvious example that I can see?
No, I don't have a counterexample in mind. I don't have a counterexample without these two assumptions for the more general definable case.
Okay, thanks. Okay, I mean, it's interesting, I think.
Okay, maybe. Do you hear me? No, probably. No?
Yes, we hear you.
Yes, yes, we do. We do.
Oh, do I understand correctly that in dimension 2 you have no loss of differentiability?
Yes, there is no loss of differentiability in Pfefferman and Lully.
Yeah.
The proof is, yes.
So may it be a conjecture for in higher dimensions or no chance?
Yeah.
Oh, that's a that's an open. That's a yeah. You try to work on that, but
Okay.
but the proof of Pfefferman and Lully relies a lot on the fact that that they work over the plane, that in the two variable case, we don't find an easy way to generalize it to higher dimension. But maybe there's another way to solve it, or maybe there's a way to generalize the proof that we don't see.
But okay, this technique of Hironaka division, which you use to extend Whitney fields, it looks for me quite new stuff. Is it correct?
No, I think that Edouard and Pierre use these Hironaka's formal division in several of their previous paper, but
Oh, okay, okay.
and there are some there are some interesting consequences of this. That's a very interesting theorem, this Hironaka's formal division. I think that, for instance, we can obtain an elementary proof of the Artin-Reyes function for power series. So yeah, that's something which is very powerful.
Okay, thanks.
You mentioned Jean-Baptiste Estenes theorem. Can you remind me what it is exactly?
Oh, yeah, I can do that. If you have
briefly,
if you have a Whitney field, if you have a Whitney field whose coefficients are C1,
yeah,
and such that are you talking about this result? I think I confused between this result or this one I used at the very beginning. Can you repeat the question?
Yes, you mentioned at some point Estenes theorem. Am I right?
Yes, but no, I'm confused.
It was close to the end of the lecture.
Oh, okay, okay. Maybe I didn't choose a good name, but okay. So if you have a field whose coefficients are C1, so the one I mentioned there, if you have a field whose coefficients are C1, and such that the formal derivative coincides with the derivative of the coefficients, then actually we have a CL Whitney field. And the idea is that at each step, and we will compare the derivative, we will be able to express the coefficients in terms of the previous the derivative of the coefficients in terms of the previous coefficients. So we will increase the regularity at each
okay.
step.
Okay. Okay. Understand. Thank you.
They have a doubt about the name. I'm not sure I used a good name.
All right. Any other questions, comments? If not, let's thank the speaker again. Thank you very much. Very nice talk.
Thank you.
We haven't planned any seminars yet, but you'll hear from me.
Can I just say something to Jean-Philippe?
Sorry?
Can I say something to Jean-Philippe?
Oh, yes, of course.
I did not use the good name. That's this theorem is called Borel's theorem. Estenes, that was the one I used there. I made a confusion with the name. Sorry for that.
So now I'm confused. So
the theorem that's called Estenes, that's the one I used there.
Yes.
and
Yes.
the theorem to extend a Whitney field. And the theorem that I call lessons in my talk, it was a mistake. It's Borel's theorem.
It's Borel, d'accord. Okay. Thank you.
Sorry for about the
No
confusion.
worries. Okay. Thank you.
All right. Anything else?
That's for me.
No. Okay. Well, thank you very much for tuning in, and you'll hear from me when we have something else lined up.
Bye. Thank you.
If any of you is interested in giving a talk, let me know. Right. Anytime.
Okay.
Okay. Have a nice day.
Thank you. Bye.
Thank you.
Bye.
Bye.
Nice
Bye.
talk. Thank you.
Goodbye.
Bye.